Okay, wow. All right. I didn't realize you guys were so excited to learn. So today, we're going to look at two things today. The first is, okay, for the entire portion of this course that we've been talking about reductions, I've only really supplied you guys with informal definitions so far. Something, a reduction is something to do with like, you can solve one problem, give it an algorithm that solves some other problem, whether or not that algorithm actually exists. And we used it as a tool to extend some very hard-earned undecidability results that we got way back when we first started looking at diagonalization arguments. And we were able to use reductions to prove a whole bunch of problems about automata and languages are undecidable, that some of them are decidable. And today, we're actually going to formalize the definition of a reduction. No more hand waving, real math now. Yeah, and there's a couple different ways that you can formalize a reduction. The current homework assignment that's out now, part 2, looks at one way. Today, we're going to be looking at this formalization called a mapping reduction, also called a many-one reduction in some other texts. But we're going off Sipser, and he calls it a mapping reduction. And then once we've sort of, and this is like, really all we're doing is formalizing intuition that we've used throughout the reduction section of this course so far. We're not necessarily going to see anything new today in that respect, as far as the definition of a mapping reduction is concerned. It's kind of just going to give you the formal language to wrestle with some ideas that you've already been grappling with. And after we introduce mapping reductions, we are finally going to prove what has maybe been, I don't know, the holy grail of the quest that was this course, the undecidability of PCP. Or at the very least, we'll start it. And hopefully we can get through a decent chunk of it today. Yeah. So any questions about what we're going to do today? Any questions about stuff that we've done recently? Anything I can refresh your memory on before we get into it? All right, cool. Then let's start. So yeah, this is just kind of a reminder of the informal definition of reduction that we've seen so far, right? We said in lecture 21 that two languages, L1 and L2, are computational problems. We said that L1 reduced to L2 if there was this algorithm that decides L2, assuming the existence of some algorithm that decides, or sorry, an algorithm that decides L1, assuming the existence of an algorithm that decides L2. And all right, let's see. I already told you that we were going to look at the formalization of a reduction as a mapping reduction, but as a preliminary to that, we need to define something else first. And that something else is a computable function. So you know how this entire time we've been dealing with Turing machines that output either yes or no, like accept or reject on its input? Well, I promised you way back when that Turing machines represented, in some sense, right, what reasonable computation was in a formal way. So it would kind of suck if our model of computation could only output yes and no for stuff, right? Because algorithms do all sorts of things. They actually find things, right? They solve search problems. Maybe you want to find out what a clique in a graph is, for example. Well, there's an algorithm that on input some graph will output a clique with some property. I don't know, the largest one. And we formalize this type of algorithm, one that doesn't involve simply outputting yes or no, with the idea of a computational or a computable function. And so if f is just some function from, honestly, these don't even need to be the same alphabet. I wrote sigma twice here, but it doesn't have to be the case. So if f is some function from strings to other strings, we'll call it computable if there is a Turing machine that computes it. Pretty much exactly what you'd expect, right? So there's some Turing machine F that for every X, which is a string in my domain, if you run F on input X, then it'll do some computation and it'll eventually halt with the output of my function on its tape, right? So I'm not interested necessarily in the Turing machine accepting a rejection. I want to know the contents of its tape when it halts. Okay? Any questions about this? Pretty intuitive concept. Yeah. Yeah. So this is actually one of those subtleties that turns out to vary with the exact type or how you formalize your reduction. As we'll see, this is the case with mapping reductions. But yeah, question in the back. I mean, if it's only on a subsection of the tape, then your Turing machine can erase everything that isn't the thing. So it doesn't matter too much. But for the purpose of clarity, let's just say that the only thing on its output tape is the answer, what the function maps your input to. Yeah? Cool. Yeah, and we will see an answer to your question a little later on after we introduce mapping reductions more. Any other questions? Good questions so far. Okay, so, all right, why have I defined this thing? Well, other than being able to capture the intuition that computers should be able to do more than answer yes and no, they're kind of essential to the definition of a mapping reduction. So I'm going to define a mapping reduction as follows. So let A be a language or problem over some, alphabet, the set of all strings over an alphabet sigma 1, and B be a language over the set of all strings over some alphabet sigma 2. So we'll say there's a mapping reduction from A to B, which we'll denote using this. I could just zoom in for a second. This sort of notation here, A, and then this less than or equal to sign with a little m in the subscript B. That's how we'll denote that there's a mapping reduction from A to B. If there is a computable function R, right, where a computable function is just this thing that we defined here. So there's some Turing machine that computes this function, such that for all X in the domain of this computable function, we have that X is in A if and only if f of X, the output of my computable function, is in B. So, oh, and yeah, this is also called a many one reduction, as I called earlier. Now you may be looking at this and scratching your head, right? Because I defined informally a reduction as this thing that solves a problem given a decider for some other problem, right? And there doesn't seem to be anything about assuming the existence of another decider here, or even really any algorithm solving A, for that matter, or B, right? So where is the reduction in this definition? Well, you can think of a mapping reduction as an algorithm that transforms instances of one type of problem into instances of another type of problem, such that membership in the problem or the language is preserved. What do I mean by that? So here's an illustrative picture of what a mapping reduction might look like. So a mapping reduction R, little r, from A to B, look, the intuition is this, right? You have, so let's say that this big black box over here represents all the strings in sigma 1 clean star, okay? And let's say this big black box here represents all the strings in sigma 2 star, okay? And we know that A is a subset of some of these strings. and B is a subset of some of these strings, right? So my mapping reduction R maps from the set of all strings in which A is contained to the set of all strings in which B is contained, such that if, let's say, X, some X that I want to map is in A, then my mapping reduction, right, it makes sure that the image of X is in B. Okay? And if X isn't in A over here, then it makes sure when it maps over to strings of this form that the image isn't in B, right? So X is in A here, if and only if Y, the thing that my reduction maps to, is in B over here, okay? And you kind of see a bit of the intuition as to why it's called a mapping reduction, because it's a map. Yeah. So, okay. Let's see an example of a mapping. Oh, and where the reduction comes in is that, remember, this R here has to be a computable function. So if I give you a computable function or a Turing machine that computes function R and a decider for B, how could I come up with a decider for A? Any ideas? Yeah. Exactly. And that works because this input to A is in, this instance of A is in A, if and only if the instance for B that I map to is in B, right? So you're like using B's decider as a decider for A in some sense by smashing this mapping reduction on top of it that transforms instances in this membership preserving way is kind of the intuition here, okay? And we'll see, I'll flesh that idea out in a moment, but I think it would be helpful to see a concrete example of a mapping reduction so far, or right now. Any questions about this before we dive into an example of one? Anything at all? Okay, cool. Well, if any question occurs to you, feel free to just yell it out. So I said that we were going to look at an example of a mapping reduction now, but you may have realized we've actually seen a bunch of examples of mapping reductions so far in the course. In fact, most of the mapping of the reductions in the informal sense were actually secretly, implicitly a mapping reduction, right? Because in what we were doing with a lot of those algorithms is we were constructing, like the ones about the Turing machine languages, right? AllTM, ETM, all these guys. What were we doing there? We were assuming the existence of a decider for the problem that I wanted to map to, right? Which had instances of the form some encoding of a Turing machine. But what my reduction did was it constructed some Turing machine first that it just fed into my decider for that problem, right? And that construction, that process of constructing an instance that has this nice membership preserving property, that was really just a mapping reduction. So as a concrete example of that, when we were proving the undecidability of AllTM last time, right? We did it in this way that involved the method of computation histories. And I kind of, as a footnote in that proof, said, there's a way you could do this similarly, sort of much more simply, right? And similarly to the way that we proved ETM was undecidable. So let's see what that reduction looks like as formally as a mapping reduction, okay? So I claim that ATM mapping reduces to AllTM. And just to refresh your memories, AllTM was the set of all encodings of Turing machines such that that Turing machine accepted all strings, right? And ATM was the set of all encodings of Turing machines and inputs such that that Turing machine accepted that input, right? So, okay, we claim that the following Turing machine R actually computes a mapping reduction. So here's how it works. So R is going to map instances of ATM to instances of ALTM, right? And the way it'll do that is exactly using the idea that we've seen so far, right? I'll construct a description of a Turing machine M to the W. And here is that description. Mind you, R isn't running this. It's just constructing a Turing machine that has this behavior, right? So on input X, we're just going to check, is my input equal to this hard-coded input W that I have access to? So if it's not, then M automatically, or M to the W automatically accepts. Otherwise, just behave exactly as M would on input X, which if you've made it this far is actually exactly W, right? And the idea for constructing this Turing machine M to the W was that we know it accepts automatically all strings that aren't equal to X, right? So what is the one possible string that it could reject? It's W, right? So we've constructed an instance of Altium that captures what we want out of a reduction, right? In particular, M to the W will accept all strings if and only if M accepts W, yeah? So, okay, now you have to actually prove that this is a mapping reduction. And when you prove, in order to prove that some Turing machine that computes a function is a mapping reduction, you need to show this if and only if, yeah? Oh, and just as a note here, the way that this would have worked before with kind of our informal definition of a reduction was instead of just outputting this or halting and displaying it on its tape, it would then feed this into some presumed decider for Altium, right? That's kind of the way we were doing things before. And so in this sense, you know, mapping reductions are much cleaner because you don't have to worry at all about the other guy's decider. You just give them an input that satisfies this membership preserving property. Okay? So when you prove, in order to prove that a function, a computable function R in this case, is a mapping reduction, you need to show this if and only if. So, okay, suppose that some instance of ATM, M to the W, is in my language ATM. In other words, M accepts W, okay? Then what I want to show is that this thing, right, R on input M to the W, which is what? Just this guy, because that's what my computable function outputs. I want to argue that if this is the case, then the output is also going to be an Altm, okay? How do I do that? Well, we know that by construction of M to the W, the language of M to the W is all the strings because, well, case one, X, the input of M to the W, is not equal to W. It accepts, right? And case two, if it is equal to W, then it just simulates M on W, but we know that M accepts W, right? So it accepts all strings, and therefore, the instance of Altm to which I map this instance of ATM, right, which is M to the W, this thing that I constructed in my mapping reduction, is indeed in Altm. It does in fact generate all the strings, right? And so all that remains to show is the other direction, right? Okay, suppose that M, you know, this instance MW isn't in ATM. In other words, M rejects W. Then by a similar argument as before, right, we know that M to the W, its language is going to be exactly all strings except the simulation of M on W, which rejects, right? And therefore, we know that the output of my mapping reduction R on instances of this form, where it's not in the language, are not in Altm. And once you've shown this if and only if, you have proven that ATM mapping reduces to Altm. Okay? So any questions about this? What we've just shown? Are we all clear? Take a sip of water. just kind of zoom out a little bit. All right. So a remark. Remember that I said that a mapping reduction maps from all strings in the language, or of ATM. Or not in the language of ATM, but over the alphabet of ATM, right? So in particular, I've omitted something here, which is that it's possible that R doesn't actually receive an input that is encoded of this form, right? And your mapping reduction needs to handle that too. But the way we defined these languages, right, is so that if ATM is looking at a string that doesn't encode a Turing machine and some input, then it should automatically reject, right? And this is very easy to handle in your Turing machine that computes your reduction, because testing whether or not an input encodes something is always decidable, right? So you can always add like a hidden step here that says, okay, test to make sure that my input actually encodes what I want, right? Some encoding of M and W. And if it doesn't, then I would automatically map to some output here that always rejects, right? That is never in my language all TM. And what I could do there is just pick some other string that also doesn't encode an instance of all TM. Yeah? It is just a technicality. But you can always assume that when exhibiting a reduction, all you need to care about are the actual instances of each problem, right? That are properly encoded. This is just kind of a note for completeness. Okay, so if there are no, yeah, and that's just the remark that I covered here. Yeah, as I mentioned earlier, most of the reductions that we've seen so far are in fact mapping reductions. And a good exercise is to go back and look at some of the reductions that we've seen so far and see if you can extract the formal definition of the mapping reduction that lies in each one, and see if there's any problems where, any reductions where you actually can't do that. And that latter point is informative for the homework. So, okay, now we formalized a mapping reduction, right? And we've formalized a reduction using a mapping reduction. Now let's formalize this intuition that a reduction should extend your decidability and undecidability results, right? So, okay, theorem, exactly what you'd expect, right? If A mapping reduces to B, okay, if you suppose that, then if B is decidable, surprise, surprise, A is decidable. And this follows pretty much exactly from the brief intuition I gave earlier, right? Okay, so let R be a Turing machine that computes my mapping reduction from A to B. Now, and I'm going to suppose, as is my hypothesis, that N is some decider for B. How do I construct a decider for A to show that A is decidable? Well, on input X, I just simulate my mapping reduction, right, using this R to obtain some Y. And then I just feed Y into my decider that I have for N. Yeah? And I accept if and only if N accepts Y. And then you do this if and only if proof as before to make sure that this is indeed a mapping reduction. But this follows immediately from the fact that N decides B, and a mapping reduction conserves membership in the way that I talked about earlier. Okay? All this to say that reductions behave in the way that we want them to, right? Or at least this formalization behaves in the way that we would want a formalization of a reduction to behave. Yeah? And so, a really useful corollary to this is that just taking the contrapositive of the last theorem, if A is undecidable, then B has to be undecidable, right? And to address Grisha's question from earlier, you can really easily modify the proof of theorem 6 to obtain that recognizability is conserved under mapping reductions as well. So if A mapping reduces to B, then if B is recognizable, A must also be recognizable. This is a nice property of mapping reductions. Okay, so with that, I think we now have all the necessary ingredients to tackle the proof that the post-correspondence problem is undecidable. I want you to picture this moment as like a save checkpoint before you go and fight some boss. Is there any question you want to get off your chest before we enter the dungeon? Anything at all? It's actually not that bad. Like, you guys have all the tools you need. It's really just a question of putting them all together in the right way. Yes. Yeah, then you take the contrapositive just the same way that you did for corollary 7, and you get the fact that it preserves unrecognizability as well. Okay. There are no more questions. All right. Let me start off by refreshing your guys' memories on what the post-correspondence problem is. Okay? So, all right. The inputs of the post-correspondence problem were sets of these dominoes, right? And a domino was just a pair of strings, one on the top, one on the bottom. Okay? Now, here's an example of a set of dominoes. And the crux of the meat of the post-correspondence problem was deciding, if you give me any finite set of dominoes, does it have this thing called a match? Yeah? And the way we defined a match was there's some sequence, possibly with repetition, of each of these dominoes, such that when I smash them all together, the concatenation of all the strings on the top is the same as the concatenation of all the strings on the bottom. Yeah? Do we think this set contains a match, ignoring these very suspicious green lines that are protruding from the bottom? Okay, yeah, it does. Here's what a match for this instance P0 would look like. So you would start with this domino, right? BBA, and then you'd use this one to get this part over here. And then, you can just verify for yourself that like the top string here matches the bottom string here. And we've drawn each of these sort of concatenations of strings from the set of dominoes that you've given me in some order with repetition, right? Because I used this, in particular, I used this domino here twice. Yeah? Okay, so the question that apparently Professor Crepeau already asked at the beginning of the course. Oh yeah, and here I just formally define what a match is. It's just this sequence where all the top strings match all the bottom strings when you concatenate them together, right? So the post-correspondence problem is determining whether, as I said, finite set of dominoes contains a match. Yeah? And this problem was interesting because it's remarkable in some sense that it's undecidable, because all the undecidable problems that we've seen so far have been these really cryptic, abstract things, right? About the encodings of Turing machines. And so for a problem that conceivably looks like something that you could encounter out in the wild to be undecidable, right? It is somehow has no mention of Turing machines, no whiff of diagonalization about the statement of this problem, right? It's just a question about matching strings and dominoes, right? So it's very curious that this problem should be undecidable, right? In light of all the the other more abstract, exclusively abstract, undecidable problems that we've seen so far. So, okay. How are we going to prove that PCP is undecidable? Well, before I continue with that, are there any questions about the statement of the post-correspondence problem? What a match is? Anything of that sort? Okay. All right. Well, if there are no questions. So sort of, I already told you that the idea for this reduction, it's going to be via computation histories from ATM. The same way that we proved all TM, we gave that one proof that all TM was undecidable, right? And in fact, that also worked for all CFG or all PDA, right? So if we remember, the way those proofs worked was that those proofs are a good example of proofs that encode a mapping reduction, right? Because you gave me some instance of ATM, right? Which was a Turing machine and a string. And what I wanted to output was a PDA, in the case of all PDA, that accepted all strings if and only if M accepted W in my instance of ATM, right? And the way that we did that, the thing that we transformed, right, in our mapping reduction, was the actual computation of M on W. And we showed a way of transforming any computation into a PDA, right, that satisfied this membership preserving property that we wanted. Yes? So we're going to do something similar here. And, to illustrate this new formalization of a mapping reduction that we just talked about, we'll do it with a mapping reduction. So the central question, that what's nice about mapping reductions is that you can forget for a moment about the decidability or undecidability of the problem that you're mapping to. All you care about is, how do I transform instances of the problem I want to reduce from into instances of the problem that I want to reduce to, right? You're somehow getting at the heart of the structure of hardness in each of the problems by relating them in this way. So what we'll do is, okay, rather than giving a reduction from ATM to PCP, what we're going to do instead is we're going to give a reduction to an intermediate problem, a slight variant of PCP that'll make this proof a lot cleaner. And then it turns out to be basically just as hard as PCP. So that variant is going to be MPCP. And it's defined exactly as PCP was, except now I just want to make sure that if P contains a match, I'll accept this set of dominoes if the match starts with the first domino in P. Because this is just some list or set of dominoes. And all I want to do is I want to make sure that I'll accept this encoding of dominoes if it contains a match that starts with the first domino. Whereas before, right, the original statement of the PCP just kind of ignored this red part. Okay, so here's a quick lemma. MPCP mapping reduces to PCP. Yeah, and this is something that we'll probably end up, we might show, I don't know, we'll see if we have enough time to do it, but this isn't the hard part, as you might imagine, right? But yeah, we'll probably show this next lecture, but for now, we're just going to use it as a black box and assume that there is some way that you can transform instances of MPCP into instances of PCP. And what's nice about this is, okay, well, now all we have to do, we don't have to prove that PCP is undecidable. If we're willing to take this lemma 11 at face value, then all we need to do is show that MPCP is undecidable, right? Which seems easier because, I mean, this is like a more structured problem in some sense. Okay, so the central question of this reduction then becomes, you give me an instance MW of ATM. Now, I told you it was a reduction via computation histories. So we want to transform a computation C of M on W into an MPCP instance, a set of dominoes P, such that C is an accepting computation of M on W if and only if P contains a match, starting with my first domino. Yeah? So how are we going to do this? Well, if my thing would agree with me. Okay, so let me just remind you of what computation looks like for a sec. Here's a computation of some Turing machine M on some input W, right? The first configuration is my starting configuration, right? And you can presume that this is one blank symbols here, but there's infinitely many more of them to represent the infinite contents of the tape, yes? So, okay. Now, in order to verify that C is an accepting computation of M on W, what do you have to do? What were the conditions that this thing here, right? These are the first configurations of an accepting computation. How about just a computation? Forget yes. Yeah. Yes. Okay, yeah. You're right in that sets are technically unordered, but you can also think of it as like designate some domino in the set, and I want to make sure that my match starts with that domino. Exactly. Yeah. But it's just kind of easier to state the other way, but you're right. That is how you would, if you were going to be formal about it, that's the way you would define it for sure. Yeah. Any other questions? Okay. So, all right. What were the conditions to verify that some sequence of configurations was a computation of M on W? There were 3 of them, right? In the case of an accepting computation. Do we remember what they were? Yes. Yeah. So C0 is the starting configuration, right? Which, thankfully it is here. And I saw another hand, Naomi. Yeah. So way down here somewhere, there's CL, and that was the third condition, and its state is the accept state, right? And then there was another condition. Yes. Yeah. Where follows means in accordance to the transition function, right? So how do we, like, you as a human being, forgetting anything about computers, how would you check? It is in fact the case that C2 follows from C1, right? Possibly, conceivably, if I didn't mention what the transition function here was, but it's not impossible, right? How do you know that C2 could be a valid configuration that follows from C1? Just like, what process do you do in your human computer brain to check this? Yeah. You want to make sure that the head only moves one space each time, right? But this could be like, I don't know, suppose this could be any string, right? Maybe it's just the word banana over and over and over again. How do I make sure that, outside of the head, the rest of these guys follow from the previous one in such a way that it's a valid configuration? Yes? Yeah. And at most, if there's at most one that doesn't match, it means that all the others, they match. Whoa, match. That's the magic word, right? Because we're trying to reduce to a problem that's about matching strings of characters. Yeah? Okay, wow, this is helpful. This is a helpful realization. We've reduced the problem of checking whether or not a given configuration is accepting, or a given computation is accepting one. If, there's a couple other things we need to do, but by and large, most of the work seems to be just making sure that at each step, each of these other characters outside of the tape head match, right? All right, so let's see how we could encode this computation of M on input W as a match. Whoa. All right, so what have I done here? Here, each of these sort of top strings and bottom strings correspond to possible encodings of a configuration, right? In other words, this guy is the same as this guy. This guy is the same as this guy. But in order to make sure that each configuration, each encoding of a configuration follows from the next, then what we're doing is this process of just matching all the symbols in a way that's consistent with our transition function, right? So in particular, if I could somehow find a way of introducing dominoes to enforce each of these matching conditions, perhaps in some way that, looks like this, right? And I've added these pound signs to delimit my encodings of configurations. Then maybe what we could do is the first domino that we have, right? In other words, the domino that we designate as our starting domino in our MPCP instance that we want to construct looks like this. It only contains the pound sign on top, and it contains an encoding of the start configuration on the bottom. Yeah? And then to make sure that now right off the bat, this means that the bottom strings are way longer than the top strings, right? So any matching that's going to be taking place is going to occur along this sort of slanted diagonal here, where, okay, if clearly I want to have a domino, in order to make it possible for this C1 to follow from C0, I want to have a map, like a domino, that makes sure that for every single character I have in my alphabet, my tape alphabet, I have some domino where it's the same character on top and the same character on the bottom. And that lets me do this matching, right, for all symbols that aren't really being modified by my tape head right now. Yes? Yeah, but we never actually do the trying, right? Because we're just constructing a reduction. We just want to come up with a set of dominoes where if there is an accepting computation, somebody else can construct a matching using the dominoes. But I don't care about that because I'm just the reduction. But yeah, this is the basic intuition. The dominoes will be designed such that they check that every single cell in one configuration follows from the previous one, right? In a way that's consistent with our transition function. Yeah. So the thing we're reducing from is ATM, and the thing that we're reducing to is this variant of PCP called MPCP, right? And the only way that MPCP differs from PCP is that I need a match in order for me to accept like a set of dominoes, right? I need it to have a match. That was PCP, right? But for MPCP, I also require that it starts with the first domino in that list of dominoes in the instance. Okay? And this is just a technicality that helps us with the reduction in a way that I'm actually just about to explain. But does that answer all your questions for now? Okay, great. Any other questions about the basic intuition of what's going on here? Now, you may be wondering, well, this would be all, like it would be really easy if every single configuration was the exact same, right? Then we just have to match one cell to one cell every single time. But the configurations, like C1 isn't exactly the same as C0, right? It differs slightly around where the tape head is. And so to account for this, we're going to add some extra dominoes that handle tape head behavior, right? So instead of adding a domino that just matches one symbol to one symbol, I'll say, okay, here's a domino that corresponds to the transition function moving right on input W1 and at state Q0. And you can see that then that domino will match, okay, Q1, the tape head has moved to the right now, and I've updated the state, and I've overwritten W1 with this symbol U1. So in addition to adding dominoes that match every single character that the tape head isn't modifying, right? I also need to add dominoes that handle the local modifications that the tape head is making in accordance to the transition function. Yeah. And there are a couple other dominoes that we need to. There's a couple corner cases with this, right? Well, okay, I've shown part of the work that needs to be done here, but then, you know, what's going on at the end here, right? Where I've matched this symbol with this symbol. Well, this blank symbol represents the illusion in some sense to my tape head that there's infinitely many cells remaining. Yeah. But, you know, what happens if I keep doing, fine, I can keep encoding, you know, configurations this way, but what if I want to encode a configuration where the tape head is all the way over here on the rightmost position and it wants to move to the right? Then what do? Well, I better have a domino that allows my transition function to do that, right? So what it might do is I'll have a domino that could match this end of tape condition with another end of tape condition where I insert another blank symbol. And this allows the total amount of tape that I'm using to increase, which is something that might happen over the course of a computation. And so you're just adding dominoes that account for all the things your transition function could do, essentially, is the way to think about this reduction. Okay? Any questions about the intuition here, what we're going to do? Because what we'll see next is the actual function, like the Turing machine that computes the reduction. That it produces this set of dominoes that mimics in this way the behavior of the transition function. All right. Okay, then. So I'm going to define a Turing machine R sub MPCP, and it's going to be the Turing machine that computes my mapping reduction. All right. So in particular, it's going to take as input an instance of ATM, because that's the thing I'm reducing from. And at the end of all this, what is it going to output on its tape? It's going to be an instance of what type of problem? Yeah. MPCP, yes. Yeah, I was wondering if I made a typo for a second there. But yeah, it's going to give me it's just, and that all that instance is like a set of dominoes, right? So you'll give it a Turing machine and an input, and it'll spit out a set of dominoes that somehow like mimics the behavior of a Turing machine. Okay. So let's see how this function is computed by our MPCP, my Turing machine. So, okay, I'm gonna suppose or decode my Turing machine M as just like the formal definition that we saw way back when, right? It's a set of states, a starting state, an accept state, a reject state, an input alphabet, a tape alphabet that contains the input alphabet and the blank symbol, and a transition function, okay? So that's just the Turing machine that I'm given, right, an M. And as this algorithm progresses, I'm going to gradually add more and more things to my set of dominoes to account for each of the possible ways that my transition function might update to consecutive configurations, okay? But for now, we'll just initialize it to be an empty set of dominoes. All right, so the first thing that we're going to add to P is this starting domino, right? Because in MPCP, we want a matching to begin with the first domino. And here, the first domino, in some sense, is going to correspond to the starting configuration of M on input W. So this domino D0 only has a single symbol, the pound sign on top, and this encoding of the starting configuration on input W on the bottom with these pound sign delimiters. Okay, so we'll throw this in. And the reason why we're starting with this is because if I want a matching to correspond to computation, like an accepting computation of M on W, then that matching better begin with the domino corresponding to the starting configuration, right? Okay, step one. We have our starting configuration down. So what else do we need to add for our matching to imitate, so to speak, a computation of a Turing machine? Well, in this step, we're just going to add all those dominoes that help us handle the matching outside of what the tape head is modifying, right? This is the very simple matching of just making sure that, okay, if my tape function's over there and it has no chance of modifying me, then I just want to make sure that that symbol remains the same in the next configuration, right? And to do this, for each symbol in my alphabet, my tape alphabet, I'm going to introduce this domino that just has the symbol on the top and the symbol on the bottom. Okay? Any questions so far? All right. Step 4. Now we got to handle the changes that our transition function could make. Okay? So in step 4, we're going to handle matching, right? Verifying that a configuration change is in accordance with our transition function when the transition function moves to the right. Okay? So for each pair of states, Q and Q prime, and each pair of symbols in my tape alphabet, such that on input, state Q and symbol red A, my transition function updates the state to Q prime, writes B, and then moves the tape head to the right. Then I will add a domino, which I'll denote DQA to P, where the way DQA works is, okay, we'll have QA, sort of the input to my transition function on the top, and we want to capture the update that is made by the transition function, right, in a matching on the bottom. So you can see I've moved the tape head to the right, updated the state to be Q prime, and overwritten A with B. Yeah? So this domino corresponds to a change the transition function makes in the configuration when it moves to the right. And we add this domino for every possible set of symbols, you know, pairs of symbols and or pairs of states and tape symbols where this can happen. Yeah? Okay. So we've handled the right transitions. Now we want to do the same thing with the left transitions. Yeah? All right. For each pair of states, Q and Q prime, and now triplets of tape symbols, and we'll see why we're looking at triplets in a second, such that same thing as before, on input QA, my transition function updates the state to Q prime, writes symbol B, and moves the tape head to the left. I want to add a domino DQAC to P, where this domino looks like this. So it moves the tape head to the left now, right? In other words, it exchanges, C is any other character, right? Whatever's to the left of my tape head, potentially. I move this to the left, I update the state, and I've overwritten A with B, right? I want to have a domino that checks that possible change that the transition function can make. Yes? Are we clear so far on all the dominoes I've added and their purpose? There are more. Okay. Up next, we're going to add Now, I made that comment a while ago where in the small example that we saw of a computation, our tape had never reached the end of the sort of little encoding that we had, right, for it. The end in the sense of the rightmost cell. So I want to make sure that it's possible for a configuration to be longer, its encoding to be longer than the previous one, right? Because in the span of Turing machine computation, one configuration can use more tape cells than the previous one, right? If I try and move my tape head over to the right, this can happen, without a second thought in the actual process of a Turing machine working. But this is something that we need to simulate in our finite encodings of each configuration, right? And so we want to make sure that it's possible for a matching or a computation to insert more space for my Turing machine to write on. And where that would happen is at the end here, right? So it can replace any one of these guys with one more blank symbol. Okay? It doesn't happen here, but if the Turing machine head were to reach the end of that sort of boundary, then it would. And for that, we'll add this domino D blank symbol, blank symbol. Okay? All right. And now there is one final type of domino that I need to add. And in some sense, it's the most important one. For each A in my tape alphabet, I'm going to add two dominoes. One that I'll call D sub A comma except, and D comma except, or D sub except comma A. And these look like this. So if whatever like implicit verifier is checking to make sure that our configuration, that our computation is valid, if it sees an accept state, then it can just forget or eliminate kind of any symbol that is to the left of the accept state. And the same thing on the right. Now, why have I added these dominoes? Because in some sense, these dominoes don't have anything to do with the simulation of a transition function or a Turing machine anymore, right? When you see an accept state in your Turing machine computation, you're done, right? But it could potentially be the case that, all right, our matching is, we've constructed a matching so far that simulates an accepting computation. But just because my accepting computation has seen an accept state, that doesn't necessarily mean that where I'm at in my matching so far, the number of symbols on the top is the same as the number of symbols on the bottom, right? Because we started, remember, our first domino introduced this imbalance, and we may not have corrected it yet. So what adding these two dominoes allows is it lets your accept state and the top eat up, so to speak, adjacent symbols. So to illustrate what I mean here, let's say, so far your matching that is in some sense isomorphic to an accepting computation looks like this. All right, so I have some characters here, and I see, there's an A before this and maybe a B after this, and whatever my encoding of a accepting configuration is. And, I have some things that match on the bottom. But so what I want to make sure I'm able to do, because, this could be, like in actuality, this could be over here, right? Because I have this sort of offset at the beginning and possible more offsets. Or it's really just the offset at the beginning that makes you need to handle this case. Is all right, well, all the symbols match so far, but the issue in some sense is that this top is still longer than this bottom. So, oh, sorry, this should be, Yeah. So this is Q accept B. You know, maybe there's some, this is B1, some symbol B1, some symbol B2 here. And then there's a symbol A1 and A2 over here. And so, all right, we found that the computation accepts. Now I want to get a match out of it. And to do that, what I'm going to need to do is I'm going to need the lengths of these strings to match. All right. And so what we allow the Q accept symbol to do is to just eat up adjacent characters. What do I mean by that? Well, the next, oh, sorry, I think I have this the other way around. This should be here. And so what we want the next kind of symbol to be, if like this is, you know, so far all this matches, even though they may have different lengths, is I want to make sure that, copy this. I can add a domino that shrinks the length, right? So if I use this sort of annihilating domino, say on A1 here, then maybe what I'll match is I'll match Q accept and A1 with just Q accept and A2 down here, or just Q accept, right? So I've gotten rid of one character or one symbol that was to the left. And the reason why I do this is so that once you see an accept state, you can keep eating up adjacent symbols like this until all you're left with is Q accept, the pound sign, Q accept. In the worst case, or just eliminate enough characters to ensure that eventually you get a match, right? That the number of symbols is actually the same as well. Again, it's one of those sort of corner case things. And now that we have added all of these dominoes to simulate a Turing machine computation, we can just output T, which is my set of dominoes. So this is the Turing machine that computes my reduction. All right. Now we're going to give a formal proof that this actually works in a second, but in the meantime, does anyone have any questions about this? Okay, I won't. Yeah, if this section over here was a little unclear, I think that the presence of these rules or these dominoes, oh shoot, that was a copy paste error. This should be switched with this. The significance of these rules will become apparent when we actually look at the proof that this reduction works, right? All right, so rather than, we're just going to kind of handle in some sense the proof that the reduction is correct, or that it is a mapping reduction, that it conserves membership in the way we want in its own separate lemma. And then we'll just use that lemma for a nice, easy proof that MPCP is undecidable. Okay, so let M, so we're going to let R be the actual function that is computed by this Turing machine here, right? So, okay, here's some Turing machine, right? Its formal definition. And we're going to let W be some arbitrary string in whatever the alphabet of my Turing machine is. And now I'll let this encoding of P here, P, be the output of this whole procedure that we did up here, right? So this thing, the set of dominoes that it contains is exactly all these dominoes that we added up here in the reduction, okay? So what lemma 17 says is that there is an an accepting computation of M on W exists if and only if it's possible to construct a match over P with these dominoes that we've added, right, in our set P that starts with D0. Okay. So, all right. Any questions about why we're proving this? What we're doing? We just want to make sure that we added the right dominoes, right? Intuitively, it was clear that we were like why we were, because the dominoes wanted to handle the matching, which corresponded to verifying that the computation, like each configuration, followed from the previous one in the right way. This proof just says, yeah, what we did actually works, Okay, so we'll handle the forward direction first, which in some sense is the easier direction because it's the one that I've been illustrating in the examples that we've seen so far. So suppose you have some C, which is an accepting computation of M on input W. What would a match D, script D here, over P, starting with D0 look like? Well, what's the first thing that needs to be in P, or in my matching over P? It's D0, right? So it's going to look, all right, well, it's going to start looking like this, right? Some encoding of C0 followed by a pound sign. And then the way we've constructed our dominoes is such that this is what a matching could look like, right? C0, I've introduced dominoes that allow C1 to follow from it in that way, right? In accordance with my transition function. And then for C1, I've introduced dominoes that allow me to have C2 follow from it, right? In the expected way. And so on and so forth until you get to CL, right? Some encoding of CL, which contains the accept state, and this guy, which contains the accept state. And if it so happens, oh, you know what I think I did? I think I may have switched the order here by mistake. I think the two guys are supposed to go on the bottom and the one guy is supposed to go on the top. Because like this part's longer, right? Just so far. So yeah. Okay, well, then you can kind of use these like inverted dominoes, because I think I got the order wrong here. To just keep canceling symbols until you're left with like this string that contains Q accept on the top and this string that contains Q accept on the bottom end at the same length, right? And you just keep adding dominoes until you can do that. And this is how you get a match D that you've constructed from your sequence, your presumed accepting computation, right? And we know that this match is possible specifically because of the way we've constructed all our dominoes, right? Okay, so now all that remains to show is the other direction, right? So suppose D is a match over P that starts with D0. And what I want to do in this proof now is, well, okay, here I was constructing a match. Now I start with a match that's the output of my reduction. And I want to construct an accepting computation now, right? The if and only if in my reduction. Okay, so how's that going to work? Well, I'm just going to, we can represent my matching D as follows here, okay? So I know that because it's a match, it's going to have some pound signs on the top and the bottom, right? And I'm just going to kind of partition it in some hand wavy sense into, I'm going to call SI whatever the sequence of symbols or characters is between the ith pound sign and the I plus 1th pound sign. Or maybe it's the I plus 1th and the I plus 2nd pound sign, because this is starting at S0 here, okay? So we know it's a match, right? That there is a match D, right? And so you can write it out in this way where, you know, like we know that the dominoes kind of cross over like this. But I'm just going to say, okay, well, if it's a match, just let S0 be this thing up here and T0 be this thing down here between my pound signs, okay? And so what we're going to do now is we're going to construct an accepting computation C of M on input W. And what we're going to argue is we're going to sort of inductively argue that each of these T0s, T1s down here encodes the Cith configuration in an accepting computation is what we're going to do. All right. So, okay. All right. So if we're going to construct an accepting computation of M on W, then we need to check those three things, right? Fortunately, and this is where, okay, he left, that guy who asked the question earlier. He was like, oh, why'd we start with MPCP? It's because we know right off the bat that because my first domino just encodes literally the entire starting configuration and just the first pound sign, then I know that T0 immediately encodes the starting configuration C0, right? So we have the base case of our induction in some sense. Right, and that was just the way we constructed this first domino D0 in our MPCP. Now, okay, this is where, let's see if I got it the right way around. So we knew when we added D0, we knew that the top of D0, that domino, had fewer or more symbols in its bottom than in its top, right? It only had that one character at the top, yes? So the only possible way that a matching could catch up, right, where the number of characters on the top and the bottom is the same, is it has to add some dominoes that have the opposite. More characters on the top than they do on the bottom, right? But there is exactly one type of domino that did that. Yeah? And that domino was this guy. It was the only domino that had strictly more symbols on the top than it did on the bottom. Yeah? You can check all these other guys, that's not the case. And so, because a match needs to have the same number of symbols on the top and the bottom, and because the only type of domino that allows me to do that are the ones that contain this accept state, I know that eventually one of these T0s has to contain the accept state, right? Because it's a match. Yeah? No, I had it right the first way around. Sorry. I was just in my head about that. Yeah, I did, in fact, I have it the right way around. And forget everything I said earlier. This is the reason why we need those Q-accept symbols, is because we know that if you're a matching, the computation you encode must have halted and it must have been an accepting one, right? Yes. Yeah. But what you can do is you can just keep appending these dominoes, right? Because you're allowed to use them with repetition. So if you have like a really, short string on the top and a really long string on the bottom that contains the accept state, then if you want to balance out the matching so that the number of symbols matches, what you can do is you can just insert, all right, like use, all of these guys to match all the symbols that aren't around the Q accept state. Yeah. And then just use these special dominoes to kind of keep pumping in characters at the top until eventually they even out. Does that make sense? Yeah, you're right. We won't be like simulating a computation anymore. But in some sense, we already know that we have an accepting computation because my QAccept state has appeared. So all I want to do now is make sure that if I have that, I also have a matching. Yeah. And so this just handles that case of getting it to an actual matching. And so you can use these QAccept dominoes, which I did in fact have the right way around the first time, to just keep pumping in characters, right, until the length of the top matches the length of the bottom. But note, you can only do this pumping if a QAccept state appears. So in particular, if my simulation rejects, this guy never appears, and I can never even out my lengths. So I never have a match. And this is the if and only if, right, that we want from our reduction. Does that intuitively make sense to everyone? Yeah? It's a good question. And that's exactly what we use over here to argue that somewhere in my matching, I've encoded an accepting configuration, right? Is because if the only way for my matching to be finite is that I use these accept dominoes, then it means that, well, eventually one of the configurations I simulate had to accept. Yeah? And so all that remains to show, we know what our last configuration is. I'm just going to call L the least I such that QAccept is contained in some bottom string here, one of these guys. And so I have my C0 and I have my CL that contains the accepting state. And so all that's left to verify is that my matching correctly encodes that each intermediate configuration follows from the previous one in accordance to my configuration function, or my transition function, right? But I mean, that just kind of, there's like a really simple, I mean, it has a lot of words here, but intuitively, there's a really simple inductive argument that does that, right? We'll just proceed by induction on I. And we know in the base case, we've already established that that T0, that first string in the bottom, that encodes C0. And the other case in my inductive hypothesis is that the bottom symbols of, or sort of whatever the bottom symbols are of my dominoes making up what's on the top here, right? Whatever dominoes make these up, whatever dominoes make up SI, also make up the next T. That's my induction invariant. And so we have that very clearly just in the way, because of the way, in the base case, because of the way the first domino D0 is structured. And sort of the way the induction works is, okay, well, suppose that the claim holds for I minus 1. In other words, that Ti minus 1 encodes the configuration Ci minus 1, and the dominoes making up the thing on top of that encode Ti on the bottom. Then the fact that Ci follows from Ci minus 1 follows just from the way that I've constructed my dominoes, right? And like, yeah. So I think we're out of time. But yeah, that basically concludes the if and only if. And then to prove that MPCP is undecidable, well, all right, I'm just going to let my reduction be, I called it F here, but I meant R, be this thing that's computed by R. And this if and only if then follows immediately from the lemma that we've just shown. Yeah. And so I sped through the end a little bit there, but like you can, like it's very easy to figure out and check for yourself that this inductive invariant is preserved, right, in the inductive step, just from the way we've set up our dominoes. Yeah. Okay, so next time we'll look at, I guess, the small issue of actually showing that MPCP reduces to PCP. And then we're in the great beyond, whatever the rest of this course is going to look like. So yeah, that's all for today.